Hello, good afternoon.
Expression is always dot py. अब अपने फोल्डर के अंदर एक फाइल सेव करो फाइल पास प्रोग्राम या पास प्रोग्राम जो भी आपको नाम मिले एंड ऑलवेज ट्राई टू
Good afternoon, everybody.
Good afternoon.
I would like to welcome Mr. Yash Sharma on the second session of the FDP. He is a blockchain professional and a tech consultant at the various university. He has an expertise in the package online training on Ethereum blockchain platform and etc. He is a consultant and architect for a multiple project like crypto projection protocol at www.blockade.com. He is experienced in the blockchain enabled supply chain, warehouse solution architect, IoT and mobility solution developer. Sir has worked on various projects like development of the bill payment processor, IoT solutions, Validex, Polycoin exchange, PayPoint, blockchain demonstration, and etc. Sir has conducted more than 30 plus training sessions in different colleges and the university. Sir, we are very thankful that you had sanctioned our time to participate us. Over to you, sir.
Thank you so much. Am I audible?
Yes, sir.
Is
You are
my
audible.
voice reaching
Yes,
you
sir.
all? Okay.
You are
great.
audible, sir.
Thank you. Thank you. Is my video fine? Are you able to see me?
Sorry, sir. Can you repeat, please?
Can you see me? Is my video
Yes,
working for you?
you are visible, sir.
All right, great. All right, so good afternoon, everyone, and thank you for that introduction. I am excited to be on this initiative where we are trying to promote emerging technologies like blockchains and some of the others in the faculty and student community. I've always felt that any technology is analyzed and examined by the industry first, and then it reaches universities once it finds acceptance in the corporate industry or software development community at large. But with this kind of an effort, newer technologies can reach student community faster, and that promotes the technology much better. Having said that, I just want to add a bit to the introduction that Sir had gone through. My association with blockchain technology is not very long. I started 2016, 2017 period. But blockchain technology as we know it, it has existed for much earlier than that. The first blockchain, which was the Bitcoin blockchain, it was conceptualized and set up in the year 2009. So it is already it's already been 13 years now, and it's a well-established concept at this stage, where the industry is developing a lot of other solutions on top of the generic blockchain platforms. So, but at the same time, it's comparatively new because it's not found acceptance in a lot of legacy technology stack platforms. So when you talk about how industry operates, it still uses legacy platforms like ERPs, CRMs, and then legacy transactional processing systems like RDA BMSs, Oracle, MS SQLs, all of those. It's not like blockchain technology is everywhere. it still needs to grow and evolve and find acceptance and use cases for the set of features that it offers. With that, let me just bring up the agenda that we have. What I would request is for the host to allow me to share screen. I have a couple of slides that I'll go through and potentially also a code demonstration if we have time today.
So give me 5 minutes. I will do the same.
Thank you.
Done, sir.
Thank you so much. It still shows disabled for me for some reason.
Let me check.
You might need to make me the co-host.
So give me 5 minutes. I will check it and let you know.
No problem.
Sir, check it again. We had done from our side.
Yeah, thank you. So I'm sharing my entire screen, not just the deck. I'm hoping to find some time to do some hands-on coding as well, but I'm not sure how much we'll be able to cover. So first of all, let me know if you can see my screen fine. I've moved myself into the presentation mode.
So it is visible.
All right, great. So this is the entire session plan that I'm sharing with you. And if we look at this, it's kind of talking about two different things. And the discussion will also treat two different branches or two different flavors of blockchain technologies as suggested here. One of the things that we need to be cognizant of is that we have a lot out here. We're talking about a lot of different things, and our ability to look at like one specific topic, if we talk about, let's say, the consensus models, or just talking about Hyperledger Fabric, that itself in-depth end-to-end discussion can take the entire time that we have at our disposal. So what I'll be doing is I will be introducing the topic at a high level, and then we'll take a look at the demonstration that either may pertain to the topic or in general. Some of these topics may be just introductions. We will not have the time to understand what is open chain platform. We'll talk about it conceptually only, but we'll definitely take a look at two big elements of this entire set, which is Hyperledger Fabric and Ethereum. And some of the things don't relate to a single stretch of the topic, like we're talking about Solidity along with blockchain platforms. Solidity is a smart contract development language. It's not a blockchain platform. So we will try to resequence some of these topics accordingly. Today is going to be about concepts only. But if I'm left with 5-10 minutes, I would like to demonstrate a very simple blockchain implementation in code also. And I've chosen the language of that implementation to be JavaScript. I'm pretty familiar with the fact that some of us may not be very conversant with JavaScript, but it essentially is very easy to follow. You just have to retain the concept in mind and you'll be able to follow the code. But I'm not very sure if we'll be able to get to the demonstration part or not. Having said that, before I jump into the actual agenda for today, I just want to make sure that I capture from you all any specific expectations or uh, any inputs that you might want to give me that will help me direct the discussion better. So I'm going to kind of open the floor for a minute or two. Anyone who wants to um, kind of just tell me what they're looking for from this training, feel free to come up with that. Anything from anyone?
Dear participants, please participate.
So feel free to tell me things like, I expect to know how smart contracts work out of these sessions, or I want to understand what is meant by consensus. It's always been very confusing for me. So some such inputs like these, they're going to help me direct the conversation better. And it could be just simple questions around how you will be demonstrating, whether it be your machine or some cloud platform. I'm fine to answer all of them. If there's anything specific in terms of, hey, this platform is not included, but I want to talk about it, we can include that also. Maybe I can cover that in some of the later sessions. This topic set that I have, it was discussed with the facilitator after a couple of back and forths. So it may not be up to your expectation. I don't know if you've seen this topic set. So feel free to tell me if there's anything additional you want to talk about. If it's brought up early on, I can include it in coming sessions. Nothing, all good. All right. In that case, let me start with a very basic idea of uh, why blockchains exist and what is the whole hype behind the idea. And sometimes it's not something that some very experienced people are also across, in the sense that they might be writing smart contracts, they might be building huge decentralized applications, but the very fact that we are operating on a system like a distributed ledger that um, is different than legacy technology, that foundation is missing. Why are we building on the blockchain and not on some of the established technology stacks? And the answer to that is kind of um, it can be derived from our day-to-day experience, although we don't really get exposed to some of the underlying capabilities that enable that experience. But it's very easy to understand once we know how a certain experience is enabled, like banking experience or uh, e-commerce websites and ordering experience, or trade finance experience for people who are in supply chains. Since we do not really always visualize what happens behind the scene, that is why we are not able to kind of relate to the idea of blockchains replacing the underlying technology stack. And one thing that I have found very useful when it comes to making the case for blockchain technologies is its comparison with a bank. So all of us have interacted with uh, the bank in some capacity or the other. Yeah, could you guys go on mute? Thank you. Sorry about that.
Sorry for the
So,
interruption.
so no worries. So all of us have in some way or the other interacted with banks. We have either a savings account or a credit card or a loan for which we talk to a bank. Now, if we think about from a technology standpoint, we're all related to uh, information and computing technologies. How does a bank operate? So it's obvious there are various technologies that are used, but if we want to just understand the core bank as it exists, it is very easy to imagine that there is a database. There is a database that has a list of all the accounts, and against those accounts, all the entries that represent your transactions or interactions with the bank. So if we talk about a modern bank, it might have your accounts and all of the entries of that account in an instance of, let's say, Oracle, which is a very popular transactional processing database vendor. And this Oracle instance, or let's just call it database, it basically is the underlying information source for all of the different channels that help you interact with the bank. So you could be interacting with the bank using phone banking, could be calling your bank for balance checks or for transfers, money transfer, or authorizing a payment, anything. The other channel that could exist is the ATM. That's I'm pretty sure automated teller machines. You all must have interacted with ATMs, or you could be walking into a bank branch. But all of these different channels, there are others as well, like online channels. You could go to your bank's website, log in there, and operate your account from there. You could have mobile banking. Your bank might have an authorized mobile banking application that lets you interact with the bank. All of these different channels, they operate on that single data store. And if we talk about it, we are able to basically entrust the bank with all our life savings by depositing our money in the bank because we trust this data store. We trust the fact that if we deposit, let's say, $1,000 today, then that $1,000 balance will continue to be $1,000 against my account next year, year after that, next year, and till the time I change that balance by adding something to it or withdrawing something or maybe transferring that money somewhere else. So I trust the bank. I'm always assured that the bank is going to keep good track of my money, an honest track of my money. And This trust is not established because the bank has a very secure data structure or a very secure um, data instance. That's one big part of it. But the other part of it is that the banks are heavily regulated. There are laws, there are regulations, there are things like audits that ensure that the bank keeps a consistent record of your finances. Having said that, every country all over the world that has a reasonably good banking system, they have regulations that drive that banking system. And then there are um, controlling banks, like in India there is the Reserve Bank. In UK there is the Bank of England. In US there is the Federal Reserve. All of them control these banks at a transactional and operational level. So just to ensure that a consumer like you are able to trust the bank record keeping systems, there is a complete infrastructure that is built that basically controls the bank, that is external to the bank. So all of these entities, they exercise their control on the bank externally. So you have all of these systems that basically track every move of the bank, how they're keeping your data. Is it secure? Is it compliant? Is it in, if there's any security loophole somewhere that they can address or remediate. So all of this governance exists today that buys you the trust that a certain bank is going to be able to keep your money secure. And then that's one part of it. The other part is the IT security. There is a very big investment that goes into keeping your data secure. There are so banks don't operate on a single data store, for instance. They usually keep redundant copies of the data, and they are kept in very secure data centers. Data centers that themselves have very strict policies of access control, resiliency, as in the data center should be able to resist things like earthquakes, flooding. It should be able to continue to function in some normal circumstances. In any case, there should be power backups, all of that. So, and then you need personnel support as well that keep that data center running. So we have this huge sort of banking industry, which runs into trillions of dollars. It is being driven by the deposits that you make in a bank, and bank using those deposits for lending or stock trading. And all of that money that the bank makes, along with all of the money that regulators kind of need to control the banks, that aggregates and add towards like trillions of dollars. Banking is a very big industry. Now the question to ask is, why does this huge industry with such massive investment exist? All it does for us is that it buys us the trust. The keyword is the trust. We trust the bank. We trust with our deposits, we trust with our loans, we trust with our liability accounts, we trust with our credit cards, everything. We trust the bank. And the reason why this trust is built up is because year on year, trillions of dollars are being spent to control different aspects of the bank. So if we, let's say, so we've talked about two things. One is the technical or IT security. The other is regulation security. If we just want to talk about IT security, that itself is a huge amount of investment for a bank. There are banks that keep 5 data centers, all keeping the same data, so that If one data center is down, the next one can automatically, can be like a fallback data center. So this entire infrastructure, it costs a lot of money. It requires a lot of manual intervention. It requires a lot of personnel support. And that's what keeps the entire banking alive. Now, let us do this. Let's try to understand this data structure that we're talking about. One of the things that this data structure or this data store type suffers from is the fact that usually, if we are just updating the data store itself, as in, let's say I work at a very big bank and I have access to their backend systems, and I go and change some data. Let's say I change the balance against my account. I might have a deposit account with the bank, and I change the balance. I just add one more zero to the balance. If I'm making that change with the right authority, the right username and password, then there's no way that anyone can recover what the previous data was. Databases are not built in a way where they maintain a history of the data. You will have to manually do that by application support coding or building some sort of trigger mechanism. But the database by itself, it does not retain updates. Then, although we have 5 data centers, but there's always a possibility that all 5 of them can be down. Someone could be, operating some sort of hardware which impacts all 5 data centers. And what that means is all my data can be lost. Now, with some of these limitations of the banking data stores, what we are trying to propose, or as blockchain community says, we can propose a system that removes all the problems of banking that need so much investment to build that level of trust with its customers. So going back to our earlier assumption, a bank is essentially a data store. It's got a lot of other things around it, like people who operate that data store, application stacks that work on that data store and make that available on mobile banking, online banking, and to service centers who are accessing that data store for customers. So all of that essentially is kind of operating on that single source of truth. And if by some means we are able to create a different kind of data store, which by design itself, as in by itself, able to give me all the features that I have to additionally add to banking, like trust through regulation, trust through audit, trust through redundancy of data, trust through data layer specific security. If we are able to have all of those features in the database itself, then what I can do is I can replace the entire bank with this special kind of data store. When we talk about this data store, what we are essentially saying, it's a chronological sequence of entries against accounts. Like it could be your account with a deposit entry that you made yesterday, a withdrawal entry that you made today. So it's like a sequence, dated sequence of entries. In accounting, we call this as a ledger. So from now on, I will be using the word ledger to describe this database or data store. And I will be calling the entries as transactions, because those are the things that you do as a part of your activity to transact with the bank. So this special ledger that we're proposing now, what we're saying is that all of the things that need to be done externally, like auditing the data store, keeping it secure from crashes, um, preventing unauthorized updates. If I'm able to build a special kind of ledger that does all of that by itself out of the box, then I can basically replace a bank. Because what I'm saying is that this special ledger actually works like a bank. You can trust it with your savings. It will never be amenable to any audit issues. It will never have any tampering or corruption. No one can destroy this data. If I can set up a database system like this, then I don't need anyone to regulate it because it's automatically doing that regulation itself. I don't need anyone to secure it because security is inbuilt. No one can tamper it. Now, obviously, the question is, how will I build something like this? And we will at some point answer that specific question. But for now, let's just assume that there is a ledger like this that exists, a software ledger like this that exists, which is able to do all of these things by itself, like a self-help sort of ledger. Then it is obvious I don't need the bank. I can just keep my financial tracking on this ledger and I can trust it. Now, the question is that to what extent? And the answer is if it's built in the right way, if all of these features are built into it as they are being advertised or as they are being spoken of, then I can trust it completely, right? So this is that special ledger that we all refer to as blockchains. It has some very promising features that that can make a lot of um, data management, data security, data audits redundant. And this is something very, very disruptive for a lot of industries. First one of those is banking and financial industry or financial domain, because all of these industries, they manage your finances by introducing a level of trust that you actually have to pay for substantially, although you don't see yourself paying it, but there is a huge industry that exists that gets paid. So if we say that using this ledger we don't even need that trust because it's inbuilt, then that entire industry, it just falls flat. And this is why blockchains are, when they were conceptualized, they disrupted the financial industry as the first target. Banks found blockchains to be a very competitive proposition, and they were kind of threatened by it, which obviously is there for good reason. Now, having said that, obviously we'll not dwell further into um, the bank's relationship with some emerging technology like blockchains. Let us now try to understand from a technical point of view, how do we make these features possible? So we've made a lot of um, uh, assertions around, hey, we can build a ledger that is self-secure. We can build a ledger that you cannot corrupt or tamper. We can build a ledger that no one can steal or damage or destroy completely. Then the problem that we have at hand is that we are, number one, building a kind of a database. And what we are saying is that this database cannot be destroyed, cannot be corrupted, cannot be tampered with, and is always going to be available and secure. So how do we do that? So first, let's look at what this database is going to hold. And we will borrow our inputs from the banking discussion. So in its very simple sense, if we talk about what a banking ledger would look like, it would be something like this. So let's say Ravi has an account, Dinesh has an account, and Nitesh has an account. All of these folks, they have account with the bank. Then there would be entries like this, that this guy deposited 200 on this date. Then another guy withdrew 700 on this date. Such entries. And these, obviously these entries are then looked at the end of the day for account matching and so on and so forth. But this is what the ledger is. And all of these entries, they are chronological, that, you know, one entry appended to the ledger after the other one and after the other one. So there's a sequence where the latest one is at the top or at the bottom. So now what we should do is, let's say we have an idea of how we can build that, you know, special or super ledger that we're talking about. The first thing that we want to do is, let's group these entries together. What we mean by that is, let's say there is a bank, and in that bank there are a lot of people transacting, and as they are transacting, this ledger is constantly being built up. What let's do is, let's decide that we will group all of these transactions together, let's say 100 transactions a piece for simplicity, and we will describe that group as a block. So what we're doing is, let's say the bank opened at 9 a.m. in the morning, and then people started sending money to someone, people started withdrawing money, cash deposits coming in, cash withdrawals happening at ATM. All of those are transaction entries. And every time there are 100 transaction entries received, we kind of put them in a block and keep them aside. Another 100, maybe 100 entries are received in 1 minute. It's a very active bank. So 100 entries, put them in a block, keep them aside. Another 100, block, keep them aside. Let's assume that this bank started just yesterday. So the first block that they got was 9 a.m. yesterday. And then every minute they started having new blocks that they keep stacking one on top of the other. There's not much difference yet in terms of how a regular ledger would work. The only difference is that we have these transactions in blocks, and each block is kept one on top of the other. So it's like a stack of blocks. Now, with this thought in mind, let us take a quick segue into what is called cryptographic hashes. Now, I'm pretty sure that you must be, at least some of you would be familiar with what is meant by hashes, but I'm assuming that we have to start from scratch. And the reason why I'm bringing up hashes is because it's pertinent to this discussion. So let's assume the process of hashing is a process of jumbling up data. What is meant by that? So let me demonstrate that with a very quick sort of demonstration of hashing technology. So let me know if you can see my screen now. I'm sharing a web page which has two boxes, an input and an output. Can someone confirm for me they can see it?
Sir, it is visible.
Great, thank you. So the process of hashing, as I said, is the process of jumbling up data, and jumbling up in a way where the original data cannot be reverse engineered once you look at the jumble. So I've got these two boxes, and I'm using a very popular hashing algorithm called SHA-256, simple hashing algorithm of the strength 256 bytes. What does this do? So in the input, I enter any unstructured data like this. In the output, it gives me the hash of that data. Now this is a very small data. For simplicity, let's make it very big. So I've added a lot of data there to make it a bit reasonable to understand. It's got all of this data that it accepts as input, and then it creates a hash. This hash is an algorithm, that jumbling algorithm that I was talking about, applied to this input data. So I don't know what that algorithm is yet. It is already built up, and the entire industry is aware of what this hashing is. What it does is it picks up this data and splits it into different segments, and then does some bit shifting of the data in binary format and then recombines it. So there are various steps to this hashing process. We'll not go into what those steps are. We'll just try to understand the process from a user standpoint. So you got this input, you got this output. Now, one thing that you understand, that you can immediately see, is that the output is always of the same length. So I can essentially add this data twice. The output is still same in the terms of length. I copy it, and now I have 4 times the data. Length is still the same. That's the first thing. The second thing to notice is, let's say I change the input by a very small amount. Let's say I remove this 1 letter. You can see that the output changes substantially. And this is one feature that will help you appreciate the complexity of the algorithm that's working there. If I change any data at any location, I add like a letter, add just a space, change a letter, the output keeps changing so substantially that it doesn't even match the original output. So I've changed like 0.001% of the data, but the output is, upside down, which means that whatever algorithm is working behind it, it's taking into factor every part of the data. Although this is huge, I've basically made it huge. This could be a million times bigger than this, and that same logic would stand. So I could actually copy paste the entire War and Peace novel in this input text. You will still see the output of this length. And if I change even 1 letter in that book, the output will change substantially. Now imagine if we were given this task of creating this hashing algorithm, how complicated it would be for us, because we are essentially ensuring that every part of the data is considered when we build that jumbling logic. So this is hashes. The process of converting this input to this output is called hashes. There are various libraries that let you use different hashing algorithms. SHA-256 is a very popular hashing algorithm. There are many others that are much better in terms of performance than this one. The Bitcoin blockchain, it uses SHA-256 today. It has been using it since it was conceptualized. So it's kind of testament to the fact that Bitcoin blockchain has never been hacked, primarily because SHA-256 is such a great algorithm. Having said that, the other very important of, in fact, critical thing to understand about hashes is, let's say this is the input, and then what I do is I create a hash of it, and I give you this hash. Then there is no feasible way for you to convert this hash back into this input. It is simply impossible. So there are a couple of things that we learn about hashes. One, that the output is always constant length, no matter what the size of input is. Two, a small change in input changes the hash. Three, there is no way for me to re-engineer back the input data by just looking at the hash. The second property also makes another property kind of easy to visualize, which is that for no two different inputs will I ever get the same output. Which means that if I have this hash, only this input can create this hash. The moment I change something in this input, something very insignificant like a letter at the corner maybe, then I get a different hash. So no two inputs that are same can give different hashes, and vice versa. Different inputs will always give me different hashes, and same hash will never be of different inputs. So there are actual formal names for these properties like collision resistance and um, idempotency and so on and so forth, but let's not go there. For someone who's just looking at hashes for the first time, this is kind of easy to understand. Obviously, we don't know how it's being done. All I want you to do is to appreciate the complexity of the algorithm that's in there. And one very important thing to understand is that it's very easy to convert this. My machine is not hanging if I convert like the input to output. So no matter what the length of input is, it's a reasonably easy compute task to convert the input to a hash. Now I'll have to request you to come back to our block example. So we are in a bank. We are creating blocks of entries or blocks of transactions. What we start doing is that every time I create a block, I create a hash of that block also. So let's say this was my first block. I don't know if I can highlight it. I actually cannot. So this is my first block, if you can see my mouse. And the first block data is all of these entries. Let's say I've just written those entries in clear text separated by this pipe. Then what I do with each block creation is I create the hash of the data of that block. So this is my entire data of the block, which might have 100 transactions. I copy that data. So let's say this is my data. Let me see if I can show it to you very easily. Let me copy this data. And what I do is just I just go here and I get its hash. I do the same thing with the next block. I copy its data and I get its hash. Now, what I also start doing is from the first block, I start adding the hash of that block in the next block. Which means, let's say my first block data was this. I copy it here. I got this hash. Let me change, I think, let's say this was my first block data. This was my first block hash. Let me copy it and let me paste it for next block. Then I go to my next block. I copy it. I paste it for calculation of hashes. And along with this data, what I also do is I take the previous block hash and I add it as data to the next block. So starting from the first block, all of my block data sets are going to look something like this. There'll be transactions and there'll be hash of the previous block. So let's say I collected 200 blocks in a day. What I basically did was I calculated 199 hashes, and in the 199 blocks after the first block, I kept adding the hash of the previous block. So it looks something like this. Let me see. Yeah, something like this. So my set of blocks or stack of blocks looks something like this. I'm placing them side by side. This block has the previous block hash plus its own data, which is the set of transactions for this block. Same thing for the next block. Same thing for the next block. Ultimately, I get to the block that I'm processing now, in which I'll have the hash of the previous block and the data that I've just collected, like the 100 transactions. Now, when I have this stack of blocks with this iterative hash linkage, next block having previous block hash, next block having previous, so on and so forth, what I've basically done is I found a way in which I can detect any tampering that happens to the historical blocks. How? So let's say I have 100 blocks, and in the 25th block, I made an entry of a transaction that was basically depositing $200. Now, what I do 2 days later, when 100 blocks are created, is I go to that block, 25th block. Anyone can change data on the block. I'm saying it's a completely transparent data set. I change that 200 to 2000 so that my balance increases. I want to steal money. Now, when I change that 200 to 2000, what happens is the hash of this block changes, which means the next block that had a previous hash when this block was good or honest, now it's going to have a different hash. Since it has a different hash, its own hash is going to change. It has a different data for that hash calculation, so its own hash calculation will change, and so on and so forth, till the time I arrive at the top block, in which I can see that now the hash is different. So assuming that there is constantly a sort of a batch process or scheduling process that keeps checking the hashes of that entire ledger every minute or every 2 minutes, the moment someone changes the hash some block past, like maybe 25th block, 30th block, wherever, the next run, which is going to check the entire block consistency, is going to immediately detect that from the 25th block onwards, there we are getting different hashes. And that would tell us that there is something wrong, some data corruption or data damage, and we should throw away this blockchain or this stack of blocks. This sort of ledger, hash-based ledger interconnectivity forms the first proposition of blockchains. We call them stack of blocks. Till now, we've been calling them stack of blocks. They are more popularly called blockchains, where there is a chain of blocks right to the very top, where each block is linked to the previous one with this hashing relationship. So all we are doing is finding a way to detect. We are not talking about how to remediate it. Once we've detected a damage or corruption, we can detect it very easily, is what we are saying. We're not saying that now what to do. So I will take a quick pause here because this is a bit complicated to understand. Does anyone have any questions, or does anyone want me to repeat what I just explained?
If any participants has any query, they can ask here.
Good afternoon, sir. Uh, Sir, whenever we have to create a particular block with the hash, there is any chance to alter it with alter by third party with another hash?
Yeah. So that chance is always there, definitely there. Anyone is allowed to alter it. The nice thing about blockchains is that you can detect that alteration. I don't know if you recall, when we were talking about databases, we said that the updates to database are lost.
Yes.
That was one of the problems that we had highlighted. Obviously, there are ways in which that can be addressed by creating some sort of update triggers, or making sure that only an application can update the data. But if someone gets access to the data store directly, let's say I'm the Oracle admin for ICICI Bank, and I decide, since I have all the rights, I have the passwords, I decide that I want to change my balance, and I have access to the Oracle RAC server. I can do it and no one will be able to find out, because that's not how Oracle is designed. Oracle does not by itself keep track of data updates. There are obviously, I'm talking about a very trivial scenario. There are a lot of mechanisms to stop that from happening. But if Oracle was operating like a blockchain, let's say if those other security measures were not in place, then no one would have been able to detect that data was updated. That's a problem that we've solved by this
Okay.
iterative hash linking. So a couple of things that I said, which are actually not done in the real practical scenario, is that every moment or every 5 minutes, this blockchain has to be constantly checked. You need to know the hash of each block and the hash of the top block. And whenever you calculate the hash of each block, and then you calculate the hash of top block, and it is not equal to the hash that you got 5 minutes back, that's when you realize there's a problem. So
Okay.
till now, we've just detected the problem. And you're right, anyone can change it. What we have enabled ourselves to do is change that change can be detected. Now, having said that, how blockchains operate is slightly different than how regular databases operate. So now we know what are blockchains. They are, this iterative data ledger where data is grouped or combined into blocks, and then each block has this hashing scheme. What that lets us do is we can detect any problem that we encounter. By problem, I mean corruption in the blocks. What to do then? So what blockchains do is that they propose creation of a network of these ledgers. So what they say is, let's not have a single copy of the ledger. Let's have 4,000 copies. An idea that's very similar to 5 data centers, but something that is much more elegant in terms of the solution. So when we talk about data centers of a bank, they are all interconnected. Data updated on one data center is sent to the others for synchronization and everything happens. But one, we are not able to understand, or we don't know what happens in the underlying communication between these data centers. Number two, they can only be, I mean, 5 is again for a very, very resilient system. Normally there are 3 data centers. And the cost that is borne by the bank for running these data centers, they are directly charged to the account holders. You're paying service fee, you're paying some cut in your interest that basically powers the bank's infrastructure. What we can do is we can distribute this cost. Let's say if instead of 5 we set up 500 or 5,000 data centers, then the cost for the bank is going to be too much. I mean, you'll basically be at a loss every time. Nobody can run 5,000 or 500 data centers. But what if that data center itself could bear the cost by getting some incentive for running that data center? What blockchains do, or what the blockchain idea is, that we should allow everyone to host a copy of this blockchain. Everyone has the same copy. So you've got 100 blocks of a ledger. Everyone should have 100 ledgers. By everyone, I mean like there should be a network in which more than 5,000, more than 10,000 systems act as nodes, and each one of them should have a copy, exact identical copy of this ledger. Now we will get to why that is important, but something that we basically solve with this kind of an architecture is that we are able to have a fallback copy. Let's see. So let's say if this is our structure and the ledger copy on this node that's been damaged. I mean, over here we detect that someone has changed the balance, so the hash is not the same. What the rest of the network can do is disregard this copy altogether and tell this node to take up or copy one of the other node's copies, which is honest. What that does is there'll always be a fallback copy. You will never be in a situation where 4,000 different systems on a network are down. Probability states 10%, maybe 15% of the network could be out, down, or crashed at any point in time. So we still have a very large number from which we can get honest copies of the ledger, which means whenever we run into a situation like this, we can just basically discard the blockchain that that does not have the right data, and we can copy from another node. Because it's so redundant and widely distributed, it is very easy to find a copy and replace ours with that copy. Having said that, let's see. The final thing, so we talked about two things. One is this hash relationship between blocks of data. The second is distributed nature of blockchains, where the copy of the blockchain is at more than one components of the network or nodes of the network, for those of us who are familiar with networking. The other thing that we need to know, and this is the final thing, is called digital signatures. Now, it is very easy to see that unauthorized people can should not be able to update the data. But how do we add data? How do we add the data to the blockchain so that it starts having blocks after blocks? So how it happens with the bank is very similar to understand. You either use your wet signatures, like authorizing a transaction using a check, or the bank creates for you a username and password using which you can use their digital channels like online banking or mobile banking, which basically is an authorization or authentication mechanism that's external to the ledger. So that username and password is not the part of the ledger. And the system that authenticates that username and password when you enter it in your digital channel, that system just creates a session for you, and the ledger does not even know about that session. It just accepts the transactions that are coming from that session. So that's like decoupled sort of an authentication scheme. What do we do in our blockchain? So in our blockchain scenario, what we have to ensure is that as data gets entered, it is being entered by the authorized person. Let's say we talk about you operating your account on blockchain. Let's say your bank had a blockchain, and what you want to say is, from my account number ABC, debit 500 rupees and credit it to account number XYZ. Now the simplest scenario is just copy that as an entry. But nowhere have we said that we ensure that it is you who is sending that transaction. Anyone could say, debit account ABC, which is your account, and credit someone else. There's no security. So how do we introduce security? So we talk about a technology which is, very widely used outside of blockchains as well. It's called digital signatures. So what digital signatures do is that they, with every identity, when I say identity, every authorized person, they get a key pair. A key pair is a combination of two kinds of keys. One is a private key and the other is a public key. So what is meant by a key? Key is a string of alphanumeric characters and numbers, or alphanumeric letters, that is used for a specific cryptographic purpose, like encryption, like digital signatures, like decryption. So for those of us who are familiar with cryptography, you'll know what these things mean. For those of us who are not, encryption is the process of hiding your data and making it accessible only to someone who knows the key or who knows the right key. Decryption is the process of making that data accessible using the right key. And digital signatures is combining some data with your key to ensure that anyone who looks at that data knows that you've also seen that data and you're basically authorizing that data. So these are some basic cryptographic functions. When we talk about a key pair, it is very easy to map it to the username and password scenario. So what we mean is, let's say if I have an online banking account, I'll have a username which would, obviously it will not be your account number, but which could easily be your account number, because usually account number is not something you keep secret. You share your account number to anyone from whom you want to receive money so that they can send money to that account. So in its simplest sense, you can think of an account number to be a username and some sort of a phrase that represents your password. So the account number can be matched to your public key. It is an entity that you share with anyone and everyone, and it can be visible to anyone. And they know that this is your private key or account. This is your public key or your identity that is publicly accessible and verifiable. The private key is equivalent to your password. If someone has access to your private key, it's very similar to someone having access to your password. They can log into your account and they can operate that account just like you would. You could send money, they could send money to anyone, they could withdraw money, whatever. So to establish someone's identity before that data is made a part of the blockchain, blockchains use this, this process called digital signatures. So the first thing that has to happen when we're dealing with blockchains is that we establish a user's digital wallet. So I'm very sure that you must have heard of this term, digital wallet. It is a combination of a private key and a public key derivative. So you can again match it very closely with your banking username and password. If you combine the username and password in the bank, that becomes your wallet that can unlock your bank funds. Similarly, on blockchains, a digital wallet is the wallet that unlocks the data for you on the blockchain. So it is a combination of the private key, which is essentially your password, and your public key derivative, which is your account number on the blockchain, or sometimes also called the address on the blockchain. So combination of these two becomes your digital wallet. For those of us who are dealing with cryptocurrencies as either traders or speculators, you must be very familiar with what is meant by digital wallets. So this private key is the important part because it is, number one, kept only with you. It's like as secure, or it should be as secure as your password. And anyone who has access to this private key basically is you for the blockchain. So let's say if you give this private key to someone, they can basically do everything with your account on the blockchain. Now, a derivative of this private key is the address. Now, the formats that you're looking at, they are very specific to the Bitcoin blockchain. In fact, this is exactly what the Bitcoin address or account that will look like for someone who has this private key on the left. So we have this key pair where there's the private key and there's the public counterpart or the public key, and that public key or some part of that public key is your account. What digital signatures do is that they expect you to enter a transaction, which would be something like this: from address to address, amount and time, if we talk about a very simple transaction that you're doing with the bank. And you kind of convert it into a format that is understood by the blockchain. So this is your address on the blockchain. This is the recipient address on the blockchain. And then you enter the amount and maybe a timestamp after it. So this is a transaction that is understood by the blockchains. If you encode this transaction, it's going to look something like this. This is the transaction data, the last box. So they're all basically the same thing with just some encoding. Now, how do you authenticate yourself to the blockchain with this transaction? So the simplest form is you send this transaction to the blockchain and the blockchain records it. No security. But what the blockchain needs to do is it needs to verify it's sent by you. So what blockchain requires you to do is take this transaction data that you just saw in the last slide, combine it with your private key and some random data, and you pass it through a process very similar to hashing process, which gives you an output, which is your signed transaction. And this output can only be created for a certain private key that is owned by you, because you're basically feeding your private key along with transaction data into the process. So this signed transaction along with the original transaction data, it's combined by the blockchain to give the address, or basically the public key of the person who is signing this data. They've not seen the private key, so they cannot, I mean, it's still secure. All they get is your public key or your address. This can be matched with your public key identity because that's public. And once that match is done, the authentication is complete. Now, this that I'm showing you here is the process of digital signatures outside of blockchains as well. For those of us who are familiar with document digital signing, this transaction data that we're talking about, it becomes a document. For those of us who file company taxes, the Ministry of Company Affairs issues a private key certificate to you, private key and a certificate. And you can sign your company's return using that certificate. The process is identical. The signed transaction is matched with the transaction data. And if they get your public key after that matching is done, then the signature is accepted. So this is the process of digital signing of transactions. We have introduced two concepts, the public and private key, that form a part of this process. And these public and private key are your digital wallet or your identity on the blockchain. Now we have talked about three different things. First, we talked about crypto hashes. Second, we talked about peer-to-peer networks or distributed network where the blockchain is stored in a very big network of nodes. And then we talked about digital signatures. To be able to understand how blockchains operate, it is completely fine. It's in fact enough for us to know only these three technologies. In fact, if I had to write a book on blockchains, very basic book on blockchain technology, then it just needs to have these three chapters: cryptographic hashes, peer-to-peer networks or distributed networks, and digital signatures. It is possible to completely understand and build blockchains using these three concepts. Now, having said that, we have about 10 minutes left. What I'm planning to do is to just demonstrate a very, very simple distributed hash ledger, not really distributed, but hash ledger, before which I'm going to let you ask your questions if there are any. So the floor is open. Feel free to ask your questions.
Hello, sir.
Yes.
So there is a one participant on YouTube. She has asked that the storage will be concerned when we are talking about the many copies when you are using a large number of data sets.
Storage. So we don't, when we talk about blockchains, the data that we store, and I'm limiting myself to Bitcoin blockchain for now, the data that we store is only transactions. And a typical block size in the Bitcoin blockchain is 3 to 4 MB. But at the same time, Bitcoin blockchain, which is a very old blockchain, it has become very bulky. So you and I, with our normal hardware, we cannot operate on the Bitcoin blockchain because it's, I think, at more than 100 gigabytes of data because it's been running for the last 12 years. But at the same time, for the scale of that data that banks or some of these large institutions operate, 100 gigabytes is not much. So when we talk about how blockchains are distributed and how different nodes on the blockchain operate and synchronize data, they are correspondingly more powerful. Their computing power is correspondingly more to ensure that they're able to manage data of this scale. But you're right. I mean, Bitcoin blockchain is very bulky. It is hard to manage for you and I with our laptops. I hope that answered it.
Yes, sir. Thank you, sir. It will be helpful to participant. Is there any
So-
question to other participants? Sir, you are saying something. Continue.
No, I was just waiting for questions. If there are none, I just want to talk about something very, very critical and then just show it. And then we'll wrap up for today.
Sure, sir. We can continue.
Okay, great. So one of the things that happens, and this relates back to the whole idea of blockchain technology. One thing that we need to understand about it is that blockchains by themselves are not a new technology, or they are not a revolutionary technology. They are basically a combination of different technologies that work together in a very innovative way. So one of the innovations that we just saw was this iterative hashing scheme. The other, which is not really an innovation, digital signatures, what that basically does is it links your public key to your account and makes them almost one and the same, which is kind of an innovation, but not something big. The one thing that can be called as, amazingly unique about blockchains is something called proof of work. I'm 100% sure you must have heard of this term, and every time someone Googles, you'll find that term. Proof of work is related to our hashing discussion. Now, what happens is that every time in the blockchain someone adds like a transaction and it becomes a block, there is a very real chance that someone adds a different block, which so we're talking about a very open network where anyone can add a block to the blockchain because it's distributed over millions of, not really millions, but thousands of computers. Then the chance that someone replaces an honest block with a different block are very high. And although I'm kind of representing this problem very simply, but it is possible for, let's say, the Bitcoin blockchain to completely be replaced by a different blockchain if this whole proof of work concept is not put in place. So all one has to do is, create an iterative blockchain with, different transaction sets and obviously different hashes, but consistent in the hash calculation, and then broadcast it to everyone on the network. If they are broadcasting it to enough participants of the network, then they will think that that's the honest blockchain and the original one is actually wrong, because they will get that broadcast from a lot of sources. If you, let's say, if it's 100 strong network and 70 people start saying that this new blockchain is the right one, then majority will win. So how does one avoid from this or protect from this scenario? So every time we add a block to the blockchain, what we propose is that there needs to be a way in which that block submission process has a step of verification that the right block is being submitted. And to do that, what that submitter has to do was, kind of adding a new block. That submitter has to create, so obviously they'll have to create the hash of the block because that's going to be used in the next block. That hashing process has to be made a little difficult so that they have to spend some time, you know, creating that hash before they are immediately able to submit it. The way that hashing process is made difficult by is by introducing a certain format in the hash. So what does that mean? So let's say if I go back to my hashing data, this is the hash that I will calculate. This is the data for which I'll calculate the hash. And what Bitcoin blockchain says is that give me a hash that has, let's say, first few letters as 0. Like give me this kind of hash. It could be any number after this, but I want a hash that should be in this format. And what you are allowed to do is take this data, along with this data, add what is called unknowns. Unknowns is a number that you add and constantly update so that you get the right output. So let's say this knowns is a number that you add as 1. The hash that you'll get is this. It's not 0, 0, 0. What you do is you change this knowns to 2. You still don't have 0, 0, 0. The ask is you reach a number, let's say a very big number, with which this entire data gives you a hash of this format. To arrive at that number, you'll have to calculate the hash maybe 1,000,000 times, each with a different knowns. So you start with 1 and you calculate, let's say, these many hashes. To calculate that many hashes, you have to repeat the process that many times. Change the knowns, calculate the hash. Change the knowns, calculate the hash. In terms of blockchains, this is called work. You have to do this work to be able to arrive at that hash. There's no way to do this work in a shortcut. You cannot, calculate a knowns for which you'll get the right zeros. You have to test, repeat, test, repeat, test. And that means you'll have to have your computer doing this calculation before it arrives at that knowns. All the blockchain does is that it looks at the knowns that you have, it adds it to the data that you're trying to submit, and then calculates the hash. If it gets the right number of zeros, your block is accepted. This process is called mining. And everyone who submits the block first, anyone who submits the block first, gets what's called mining reward. Now, this incentive for submitting blocks is the only innovation that's there in the blockchain technology. All the other stuff that you see around digital signatures, peer-to-peer computing networks, they have existed much before blockchains. Digital signatures and cryptography was there in World War II. Peer-to-peer networks were there in 1990s. Napster, Torrent, they were all distributed networks. So blockchain did not invent anything. The only thing that they invented was this knowns scheme. So using this knowns, if you're familiar with JavaScript, you can build your own blockchain. The very simple thing that you have to do is you implement proof of work in which you capture a number called difficulty. This difficulty is the number of zeros that you want. The more the number of zeros, the more difficult it is to calculate the hash because you'll have to repeat the process that many number of times. So you created this crypto block which has some block data, indexes, which block it is, timestamp, some data, preceding hash, this is important, and the current block's hash. And then you've got the knowns which you will initialize to a certain value. Then there is a very simple compute hash function. It basically combines all this data together and then returns the SHA-256 hash of this, which is basically a use of a predefined library. So what you do is you create the first block, which is called the genesis block. You define a difficulty level. 5 means 5 zeros. Your hash should have 5 zeros. Then you define some data. Since this is the first block, the last hash will be 0. This is a timestamp, and then some data which could just be text. And then this one is that repeated check, which checks the entire blockchain for its validity, mapping it with the latest root hash. And this is where the blockchain starts. You create a class of the blockchain, and then you start adding 2 blocks. You added 2 blocks here with 2 different types of data. So this data and this data that you're trying to add, which basically is essentially trying to represent a transaction, but it's just a JSON object. So when you run this code, you'll be able to see how typically blockchains operate. So I've given the difficulty level of 5. Let's reduce it a bit so that my computer doesn't crash. Okay, I have 4. So as you can see, it's repeatedly calculating the nonce, and I don't know if you can hear it, but my CPU is heating up also. This is at difficulty level 4, where it's looking for unknowns to submit a block, which gives it a hash of 000 blah blah blah, like 4 zeros. If I had 5 there, this will take much longer, maybe an hour. Now, Bitcoin blockchain is at a very different difficulty level. If you look at the blockchain explorer, you can do that by going to blockchain.com explorer. These are the blocks, latest blocks. These are the transactions that are becoming parts of the block. If you look at this block, look at the number of zeros it has. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 19. So the difficulty level is at 19. So it's calculated with difficulty level 5. The nonce that I had was this, and the hash of the block is this with 5 zeros. The next block was at this 5 zeros. Now imagine how much time it would take for 19 zeros. So I would encourage you to kind of explore this concept a bit further. This is a very important part of how blockchains are made secure. Proof of work ensures that a very powerful mechanism that basically calculates the hash is, put at the disposal of block submission process before it becomes a part of the blockchain. So having said that, we will wrap up for today. If you have any questions, suggestions, or thoughts, feel free to bring those up. Okay, there are some chat questions.
Participants are requested to share their thoughts for today's session.
Okay, there's one question. Is it possible for a non-IT or computing background person like me to understand? Yeah, it's definitely possible. It's not a very difficult concept. Among all the emerging technologies, you've got AI, robotics, RPA, quantum computing. Blockchain is the easiest one to understand. If you want to become an AI engineer, 6 months is the minimum you need to become even a beginner. But 6 months of learning, like maybe a framework like Ethereum, which is a very popular one, you can become an expert. So definitely open for you to explore from whatever background you are. Any other questions?
Is there anyone? If anyone has doubt, they can ask.
All right, if we're all good, then let's wind up for today. Let's connect tomorrow. Feel free to think of questions if you come up with some, and then we can discuss tomorrow. Thank you all.
Hello. Am I audible to everybody?
Yes, sir.
If any participant has question or the query, they can ask over here. Otherwise, we will wrap up this session. Thank you very much, sir, to share your valuable time as well as the knowledge with us.
Tomorrow we have 10.
We will meet tomorrow morning at 10 a.m. Our speaker will be Dr. Shandip Tanwar. Okay, wish you all have a great day. Thank you very much, sir. Again, we will wind up our session over here. Thank you, everybody.